The complete story, spoken version in English. If we go back to the very foundation of physics, there are really just two famous laws that describe almost everything we observe: Newton's law of gravitation and Coulomb's law of electrostatics. Newton wrote F equals G frac m1 dot m2, R Coulomb wrote equals K frac q1 dot q2, R squared. They look almost identical: a constant G or K, two quantities describing the interacting objects, masses or charges, and a distance R between them. The classical explanation: in classical physics, the idea is that the effect of one object spreads out over a spherical surface. The surface of that sphere grows with r squared, so the intensity of the effect decreases with 1 r squared. That's why both Newton's and Coulomb's laws contain this 1 r squared term. The effect gets weaker with distance because it is distributed over a larger surface. In short, it's a one-sided interpretation, as if the effect goes from object 1 to object 2. The distance r is seen as the distance to the source. The interpretation you give that you say that picture isn't quite right. The effect doesn't spread out from a source. It arises between the two structures at the same time. There is no sender and receiver, only mutual interaction. The distance from structure 1 to structure 2 is exactly the same as from structure 2 to structure 1. That's why we use r squared. It's one distance, but acting in both directions simultaneously. So r squared doesn't represent dilution, it represents the bilateral nature of the interaction. Two equal but opposite relations that together form a single effect. The formula therefore doesn't describe a one-way influence, but a shared acceleration. Where the mistake began, the force F in that formula is the total interaction between the two bodies. Yet in F equals mc dot A, we apply that same F separately to each body. We write A1 equals frac F m1 quad text quad A2 frac FF m2, as if each object experiences the full force. But that's not true. That F belongs to the system as a whole. In reality, the formula gives the total relative acceleration between the two bodies, the rate at which the distance between them changes. That total acceleration must be bilaterally distributed between them in proportion to their masses. A1 equals A text total C dot frac M2, M1 plus M2, quad text quad A2 equal frac M1, M1 plus M2. The larger the mass, the smaller its share of the total acceleration. The lighter mass moves more, the heavier mass less, perfectly symmetrical. Example: the apple, the earth, and two apples. In everyday life, everything seems fine. When an apple falls, it behaves exactly as Newton predicted. But that's not because nature literally follows our equation. It's because we ourselves are part of the system we're measuring. The apple and the earth. When an apple falls, the apple and the earth attract each other. The apple clearly accelerates downward, but the earth actually moves upward ever so slightly. The ratio of their accelerations is inversely proportional to their masses. Since the earth is about 10 square 24 times heavier than the apple, its motion is 10 through 24 times smaller. Our measuring instruments are fixed to the earth, so they move along with it. That means we never measure the individual accelerations, only the combined effect of the system. From our perspective, it looks as if only the apple moves, but an outside observer, say someone watching from space, would see that both are falling toward each other, the apple quickly, the earth extremely slowly. Two apples interacting for Faradayam. Now, if we take two apples, each weighing 1 kilogram and 1 meter apart, their mutual gravitational force equals G, about 6.7 times 10 to the minus 11 newtons. That's incredibly small, so small that it's completely overshadowed by the Earth's attraction, which is roughly 10 newtons per kilogram. Their mutual acceleration does exist, but it's totally drowned out by the much stronger pull of the Earth. Even if we wanted to measure it, it would be practically impossible while standing inside the Earth's reference frame. The consequence. In the first case, Apple and Earth, we don't see the effect because we move with the system and therefore measure only the total motion. In the second, two apples, we don't see it because the effect is far too small compared with the Earth's influence. It becomes visible only when the masses are comparable and no dominant third body interferes. That happens on the very smallest and very largest scales, where the masses within a system are of roughly equal magnitude. And that makes perfect sense. The interaction strength increases rapidly as distance gets smaller, because according to Newton's law, it grows with 1/2 r squared. At those tiny separations, the Earth's influence, however large, becomes relatively negligible. Two nearby, comparable structures then experience each other's interaction far more strongly than the pull of any distant heavy mass. So, at equal masses and short distances, the hidden symmetry error becomes visible. And that explains why deviations appear both in particle physics and in clusters of galaxies. Because our formulas don't distribute acceleration bilaterally, but treat each object as if it receives the full force, we end up applying corrections to make observations fit. In quantum physics, we call them probabilities and uncertainties. In cosmology, we call them spacetime curvature. Yet the underlying reason is far simpler. The acceleration should be shared. Would you